30 seconds delay for the other one. Sometimes I have to pause it here for a second. Okay. Seconds. Yeah, you see, delay. I have to mute. Otherwise, you have an echo because I have two things going on. Okay. I think you can see that. I'm going to use my trusty thing here. Okay, good. People are coming in a minute. Perfect. All right. Thanks about time. All right. So let me start welcoming everybody back again to the online SPICE and SPIN+X seminars that I lead here in collaboration with Alexander Mook, which is now in Münster, Lieber Schmeckian in Dresden, Angela Wittmann here in Mainz, and Karen Ebersol sitting now in Duisburg, in collaboration with SPIN+X Collaborative Research Center that is led by Martina Schliemann, Burkhard Hillebrand in Kaiserslautern, and my colleague here, Matthias Chloe, in Mainz. As you know, this is a webinar format, so please write your Q&As on the chat or on the Q&A box during the talk, and then after the talk, we will give you the floor to ask the questions to the speakers and bring you to the panel if you have further questions. Today, it's a pleasure to invite Yossi Paltiel. So he's a professor at the University of Jerusalem, Hebrew University of Jerusalem. He is from Weizmann graduate and also a PhD. And he has many expertise in our field and many prizes. For example, the Fritz Prize for Advancement in Science and Education, and the K Innovation Prize as well. That I know of well, and the most recent one is the Love for Climate Energy award, which is interesting. So it's a climate award. I never seen a physicist having a climate award, which is also great. But he's particularly been at the forefront of one of the very hot topics in our field, which is this chiral-induced spin selectivity that started originally from Israel, in fact, and this research from Ron Raman and himself. And has been a fantastic breakthroughs. And then I've been having the pleasure of having listened to some of his talks during some of the workshops, and I really asked him to come and bring it to our community, broader community. So with this, I'll ask you to please go ahead and share your slides with us and begin your talk, and I will mute myself here to give you more bandwidth. Okay.
So thank you very much for the invitation of being here in this. Just let me see. You taught me, but I need to remember how to do that. In this nice seminar. Just a second. Okay, so I'm happy to give this talk. Please, if you have any questions, because I know that CISS is, there already one thing in the chat, but if you have any questions, any remarks, please ask. And I will try to answer during the talk, because I prepared a lot of material because we have done and relating the CISS to spintronics, but and I know that there's some controversy and some questions that I would be happy to answer while talking. So I'm Yossi, I am from the Hebrew University. I'm also now the Dean of Science. I hope to finish this within a year or two. But I want to thank my collaborators. I have a large group, but my collaborators, which are many, Rona, Aman, so will give an additional talk here, Oded Milo, Jason Robinson, Angela, Matthias, who also are part of the organizing, Stuart and Thomas and many others. So I want to start this talk talking about chirality. And chirality, as we all know, is breaking, or we have the breaking the mirror symmetry, or we can break the mirror symmetry where we cannot superimpose the right or the left, or it's this kind of symmetry, which is very common in life in all the world. And we cannot superimpose one chirality on the opposite chirality. And of course, as I will talk, chirality manifests itself in many things in life. And I want to claim that chirality by itself is something which is very interesting, but it's a force in nature that we should take into account, and it allows some breaking of symmetry in nature and will also help us in spintronics. I see Dimitri Butker here, so we'll talk about breaking the chirality or the weak forces. So in principle, chirality is wide, and of course there are many structures with a chiral, but I want to connect two structures, the ones which are organic chiral, or the molecule of the biological world, and the motion of the electron spin under electric and magnetic field, which will also be chiral. When you force an electron to go under electric field and magnetic field, you will have a chiral motion. When you switch the magnetic field, you will have the opposite chiral motion. We will also address this nice feature, which is the snail, which is a mix of organic molecules and oxide, and it's also chiral in the larger scale, and I will try to claim that this is also something we'll want to mimic when we do spin-like devices. So in principle, as I told you, chirality matters in all scale, but mainly in life. Life, when we talk about life, life is homochiral, meaning all of the peptides are left side of chirality, breaking one kind of symmetry, the sugar is the opposite, but it doesn't really matter that we have only homochirality in life. And one of the questions we wanted to address early on when we did this study is why is the world of homochiral, but when you do chemical synthesis, you have both chirality, both left and right. And even more important, why was the symmetry breaking preserved, and why do we prefer the energy? So we think, and this is, I know that some claim that if you break the symmetry because of interaction, the symmetry should be preserved, but we think that the answer is spin and spintronics, and this is why I was happy to give this kind of seminar. And actually related to the CISS effect, the chiral-induced spin selectivity effect, which was when we started a little awkward or little side community, but becoming more and more popular. So the chiral-induced spin selectivity effect is when you force an electron to go through chiral structure, the chiral is small enough, you have an effective magnetic field. And this effective magnetic field is due to the forces that force the electron to go, the single electron to go through this chiral structure. You can calculate this effective magnetic field, and you have opposite effective magnetic field if you go up or down. So in principle, you should prepare or expect spin selectivity whenever you go through chiral structures. So why, if you start with two spins, you will have only one spin going through. If you have one chirality, if you have the opposite chirality, you have the opposite spin going through. If you take the opposite direction, you switch the spin because you need to force this centrifugal or spin orbit coupling forces. So in principle, this is a chiral-induced spin selectivity effect. You can get the same effect with non-coherent transfer. If you have multiple scatterings, the scattering is also spin-dependent in chiral potential because you preserve angular momentum, and you will have also spin selectivity. So in principle, this is the effect, and the effect seems to be very general and very simple, but we have some problem with the effect. First of all, you should ask yourself, is it a spin polarizer or a spin filter? Does the electron which goes through the chiral structure become more and more spin-like? Only half of the electrons go through. It doesn't really matter because we always couple to a bus which mix the electrons quite fast. So it's always we have more, all the current goes, and if the chirality or the effect is strong enough, we have spin selectivity. The other thing you should ask, okay, I understand that we have an effective magnetic field and the effect is working, but then you can ask how large is the effect, and why and how do we get such a large spin selectivity if we have very small spin orbit coupling? Because we did the effect was first found by inorganic molecule, which are light atoms and has very small spin selective processes. So in that sense, I will address this more in additional slide, but it's not the simple picture to understand how the CISS work is always easy to understand, but does not give the right magnitude of the effect. And then now we are 30 years after finding this effect, and still this controversy because of the magnitude of the effect that experimentally it's so strong. While by theory, if you do simple single electron picture theory, you'll find it much weaker than what people usually find. So by doing this effect, we first of all, why doesn't work? By understanding this effect in the classical mean, we can start to go, first of all, to the origin of life, saying why, one of the reasons why it is important to life. The other reasons relate actually to green energy. And if we'll have time, I will address that in the end. But one of the reasons is that you give it, like all spintronic devices, we give it angular momentum. The structure for the electron wave function to have angular momentum. The angular momentum is preserved and more immune against scattering, like the rotating football where we throw. The Super Bowl was just a few days ago. So like the rotating football. And then we are more immune against changes in environment. So as we are talking about spintronics, we can get a much better efficiency, or we don't want protein to conduct, but we want any electron that start to reach the end. But before going on to spintronics, I want to address the main question that people are asking about CISS. And here, if there are questions, please write them. I would say the CISS effect is much more complicated than what we say by this hand-waving argument. First of all, it's a multiple electron effect. It's a multiple particle effect. And actually, if you want to compare it to metamaterial, it's a non-local effect because the electron wave function above the Fermi energy and the few electron volts which we give them, you work with large polarization, and so it's a multiple particle effect, and it's a non-local effect. So in principle, you induce much larger effective spin-orbit coupling than what you expect. And if you want to see that it's non-local, you can compare it with the optical activity. CISS effect and optical activity, or CD, are much alike. The CISS effect is always is related to the lower band of the optical activity. So in a sense, I would say we have an effective spin-orbit coupling, which is much stronger because the electrons come with a high energy. They get closer to this chiral structure. We induce large spin-orbit coupling because of this scattering effect, you can say. And this scattering effect, depending if it's low temperature or high temperature, but if it's high temperature or room temperature and you want to preserve angular momentum, will involve chiral phonons and dissipation. So in principle, you will enhance the CISS effect, but you also expect dissipation. So it's not that you break time reversal symmetry, but you don't have time reversal symmetry because of this kind of dissipation. And this is the same thing when you put a molecule on the surface and you get the MEPAC effect, which I'll address later. You have fluctuation, you have a polarization, it's a multiple particle effect, and then you have a spin-spin interaction. So getting a CISS theory is quite simple, a single particle picture. Getting the full, but this will not give you the right magnitude. Getting a full CISS theory will need a multiple particle picture, we need a dynamical picture, we need spin polarization, we need polarization vector, which is very hard to achieve by standard theoretical approach. And this is one of the major issues that we have in CISS, and one of the major things that we need to improve in the CISS community. But let's say now we believe that we have the chiral molecule, or we have a very small chiral structure, and we have very efficient spin polarization. Then I can say, like any spintronic devices, we can use this kind of effect to have spintronic devices, or to develop spintronic devices. And those spintronic devices actually will be very efficient because we can get almost 100% spin polarization by very short time. It's much more efficient than spin torque transfer or other mechanism of getting efficient spin current. They can also simplify the way we build spintronic devices. So in a sense, I would claim that I'm not saying that spintronics is meaningful, but I would say we can also use chirality and spintronics to get better spintronic devices. And this is what the aim of this review that we wrote a few years ago to Nature Review Physics. So spintronics in general, people are using giant magnetoresistance and tunneling magnetoresistance. So in general, you use two magnets for those kind of memory devices. And you can switch by spin current or one of the currents of the devices and have a large resistance or small resistance. And in principle, you can get a memory devices. What I try to claim that using chiral molecules or chiral structures, you can remove one of these magnetic layers, getting a much simpler structure, but you can get also very efficient spin polarization that can be used to simplify spintronic devices. And this was one of our goals for many, many years. So what I will show, it's not the collaboration with Dima, but the collaboration with Matthias and others, and Stuart, I showing that if we can couple this spintronic, this is a skyrmions or a spin structure, a topological spin structure, and we want to couple our chiral molecules to those kind of spin structures. So when we talk about spintronic devices, I think we are getting there, or getting CISS into spintronic devices. I think we are getting closer and closer to our goal, because we can also write and read. We did many memory devices, and not only our group, but other groups as well. We were able to show that some of the memory devices work at 200 Celsius, very close to IT technology, and they are oxides. It's not the 500 C that are needed. We did also some MOX and DMOX spintronic devices using this kind of CISS effect. And we can enhance memory density. We can do also efficient interconnect. I will try to address any of those things to show several examples to show why I think that CISS is important for spintronics. So first, we will try to do a memory, a different kind of memory device, a memoristor, which is made of spintronics. A memoristor is a memory and a resistor. You have both, this is the IV, and you have nonlinear IV, but you have also the two level which you have in the memory devices, and the change in resistance, and you have an hysteresis, which could act both in a memory and a resistor. This is quite good for embedded memory. And we try to do a memoristor kind of a device using the CISS effect. So one of our first attempts was very simple. We took barium ferrum oxide nanoparticles. Those are very strong magnetic nanoparticles. The coercive field is about 1,000 Gauss, so it's a very strong magnetic particle. We did a chiral layer. This is an organic chiral layer. And we try to remagnetize with outside magnetic field the particle to be upward or downward, and we measure the resistance inducing currents going from from bottom up, let's say, and we try to see what is the resistance. So in one case, we were injecting to the majority of the spins, in the other case, to the minority, and we saw difference in resistance. So here is one case we have to the majority, we have high resistance, so we have low current by changing the voltage. The opposite case, we switch the magnetization of the particle. We have a lower resistance and we have higher current, and we can have a two-level system. It's kind of a memoristor, but it's a memoristor with using external magnetic field, but it's a very simple kind of a device, and this was just showing that in principle we can use a magnetic particle and very simple devices to do this kind of memoristor-like memory. You can draw a very nice picture and publish it in advanced material, but it's a very simple kind of device. If you want to go smaller to single particle devices while switching with internal magnetic field, You can go build this kind of devices. This is a very narrow gap, a gold contact, and you have very, very small gap. You put chiral molecules on top, and then you put the particle, this is a 30 nanometer magnetic particle on top. So this particle has very high coercive field. It doesn't change the magnetization, but the gold with chiral molecules become weak ferromagnet, and we can change the magnetization of the gold with current depending on the spin we are injecting or injecting. So in principle, we can switch the magnetization of the particle and be aligned with the magnetization of the gold or misaligned and get, this is an actual device about 30 nanometer in size, or the active size is 30 nanometer in size, and you can get a memristor-like behavior switching on and off just by putting a single particle on top with a magnetic moment and with driving current, and you can get a memristor-like behavior in a two-state logic kind of device in a single particle at room temperature using these spintronics devices. So everything I showed so far, it's at room temperature, ambient condition. You can have a humidity and everything else. It's a very simple kind of device. The other thing that we have tried to show is that people were saying, okay, it's organics, and you go talk to Samsung or other, and they say, okay, can you do a memory device? They say, we don't want to work with organic, we work only with oxide, and we want it to be stable up to high temperatures. So in principle, what we have done, we try to do chiral oxide mimicking the snail I showed you at the beginning. And the thing is that you can grow aluminum oxide or chiral aluminum oxide by doing a combination of atomic layer deposition and molecular layer deposition, layer by layer. And this is done in collaboration with Roy Yerushalmi. And we do use the organic was alinol, amino acid, which is chiral. And the atomic layer deposition was trimethyl aluminum. So we have an oxide layer and an organic layer, and we can go layer by layer at the atomic layer deposition and get about 5 nanometer of what we call chiral oxide. And then we can characterize it, and we saw that we have both the chiral molecules and the oxide. We can have different relation between the chirality and the oxide. The higher oxide ratio, the stable it is at higher temperature, the lower the spin polarization, the spin effectivity. So when we published the paper, we did 1 and 1, one chiral layer to one oxide layer, and this was stable up to 150 Celsius. But what we saw that with this 5 nanometer kind of device, we get almost 100% spin polarization, which means it's a very efficient layer. You get, this is a current without, this is one magnetization, this is the opposite magnetization for one kind of chirality. And the spin polarization is defined, you choose a voltage, let's say 1 volt, and you take the current for up magnetization minus the current for down magnetization divided by the sum, and this is almost give us 100% spin polarization. If you switch chirality, you get the opposite effect as the minus is higher than the sum, and again, if you take the absolute value it's 100% spin polarization. You can do a mix of two kind of chiral molecules, and you don't get spin polarization at all. Which says that the chirality itself is giving it this high value of spin polarization. So far, it's a very effective device. So far, I hope I convinced you that this effect work. It's important for life because you have spin polarization. You have a single line of spin polarization. But it's also effective for spintronic devices because it can give you almost 100% spin polarization with 5 nanometer kind of devices. In principle, can work at very high temperature in a very simple kind of structures. So I say, okay, so what can we do with that? Can we use alter magnets? This is what we try to do with gyro, but we didn't start it yet. But we have other material like paramagnets, ferromagnets, antiferromagnets, superconducting, and other kind of devices that if we ask ourselves, would this effect work, or can we do devices of spintronic devices using all this kind of structure? So I will tell you the short story, and then I will give you, I will ruin the points, because I will tell you that any time you use chiral molecules on any of those structures, I didn't try altermagnets, but you will see a change. You can have very small paramagnet or super paramagnet, which are small particles, and then the magnetization will be random. When you put chiral molecules from one side, you will get a ferromagnet. You can get, I will show a work we have done with Matthias and Angela Whitman, where we did coupling between the chiral gating, the organic chiral gating, and the skyrmions, and the skyrmions, ferromagnetic skyrmions. I will show work with Stuart Perkins about anti-ferromagnet. I will not show the work we have done with Jason Robinson and others about superconducting, where we put chiral molecules on the superconductor, we get the triplet states, and I will not show other kind of works that we are related. But whenever you get these chiral molecules involved, because of the large spin orbit coupling, you will get a very strong effects. So this is an experiment we have done. We have done a few years ago, and this is putting chiral molecules on a ferromagnet. There's also the molecules on a ferromagnet at different scale and size. And this is now, when we started with this, people were saying it's breaking time reversal symmetry, so it's quite hard to understand. Now it's highly cited. But it does break somehow time reversal symmetry because of dissipation and fluctuation. But what we did, we put L amino acid, L polyalanine, it's a polypeptide, or dipolypeptide on a ferromagnet. It's a very thin ferromagnet, and we could switch the magnetization either to be up or down just by absorbing the molecules on top. So we put the molecules on top, and then most of the ferromagnet was switched to up magnetization. This is the atomic force microscopy measurement. We can put the molecules on opposite, and we get the opposite magnetization. You can measure a anomalous Hall effect. It's acting like a magnetic defect. You drive current, and you get, for one case, one kind of a Hall effect. In the opposite case, you get the opposite kind of Hall effect. So you get really voltage differences because of the absorption. So this is now a well-cited work, but I have to be cautious, because you need to have you need to understand that we have it's a surface effect. And we have about 10 to the 13 molecules per centimeter square, which means that even if you pass a full spin and you have thermal fluctuations, so it's acting like a spin dipole, it's a very small spin. It's 10 to the 13 spins per centimeter square. So it's a very small effect on the surface. So you need to choose a substrate right. I get emails, people asking me, why did I take nickel, about 100 nanometers of nickel? I absorbed the chiral molecules at top, and I didn't see the switch of magnetization. What we chose here is, after careful consideration, and maybe we should have written it in the original paper, because I get many emails asking about that, it's a cobalt gold, and it's a very thin cobalt. The easy axis is out of plane, but it's almost a thickness where it can go in plane. So it's a very flexible kind of cobalt. It's very thin, and this is why the chiral molecules can switch the magnetization. So it will not, it's a surface effect, and this is how you should address it. And it's a weak effect, because it's related to the density of the molecules, but it is an effect. It's somehow called the MIPAC effect. We gave the name, but I don't think it's a good name, but it's related to this. If you want to measure how strong is the effect, this you can do with a very simple, it's a complicated experiment, but the idea is very simple. You take an AFM tip and measure the force, you put some kind of spacer, and then put in chiral molecules. Then you approach a magnetic surface, and let's say it's a magnetic surface, but it's a flat, on the top you see only gold, so it's a flat surface, and measure the interaction with the surface. And because that you have spin polarization of the molecule, whenever the molecules get closer, you have electrical polarization. Even if it's chiral, it's related to spin polarization. So because you have spin polarization on the surface, it will interact with the magnetic substrate. You can have either a triplet-like kind of interaction or singlet-like kind of interaction. So in principle, we claim that there will be a different kind of force attracting to this magnetic surface depending on the magnetization of the surface. So it's like an exchange microscope. The forces here are exchange microscope, or if you want to go a little bit shorter, longer in range, we have also work about that. It's spin like Van der Waals interaction, but you should measure a difference between up magnetization and down magnetization, and this difference is about 150 milli-electron volt, which you can calculate to an energy of tens of kilocalories per mole, which is like hydrogen bonding. So this spin exchange interaction gives you very short range interaction with the surface, and this short range interaction generate exchange interaction. Those exchange interaction can be stabilized with the surface. That's why when we use superconductor, we get a surface triplet-like, chiral triplet-like structure. When you use power magnet, we can turn it, if it's thin enough, to ferromagnet, and that's why we can interact with that kind of case. So we wanted to use this kind of interaction to have some kind of spintronic devices, and what we did is the chiral-chiral interaction. We have a joint collaboration. It's called the HIMES. How, I don't remember the abbreviation, but it's how we can couple chiral to chiral, and we use a Kerr microscope that we bought from Chemnitz, from Germany, from IE Magnetics. And you can, and samples we got from Matthias Kalui, and we can measure the magnetic domains, how they have stripes domain, we have stripes or skyrmion domains, and we try to measure magnetization using this kind of microscope. But first, I wanted to answer one of the questions that I asked in the beginning, is how I told you that if the symmetry is broken, it's important for biology because you want to preserve angular momentum, and angular momentum is more immune to scattering because of spintronics. I want to just address one possibility of how the symmetry was broken, and this is when you put RAO, which is related to the origin of life, or you put chiral molecules on top of magnetic domain, you change the hysteresis loop. You have coupling between the chiral molecules and the magnetic domain, and you can change the hysteresis loop. So in principle, we had two kinds of papers which relate to that. We had a paper which says if you have a magnetic domain, they will interact more strongly with one enantiomer than the other because of those spin exchange interaction. And we have the opposite that we have, so we have the opposite that we switch magnetic domain because of this interaction. So we have some kind of avalanche kind of mechanism. So if you believe that RNA precursor relate to the origin of life, then we have a mechanism that says that if you have a magnetic surface, you will choose only one kind of RNA precursor than the other, only one kind, depending even small asymmetry will break the symmetry by large. Because of this avalanche process, you will start with a small domain, absorb only one kind of RNA, then as the domain will enlarge, you will absorb more, so you'll have a way to break the symmetry. And there are the group of Dimitar Sasilov and Furkan claims that in lakes in Australia, you have magnetic layers on the bottom, and those are enabled to break this kind of symmetry, and maybe show that this is related to the origin of life. But this is just an anecdote for this, but we can use the same effect to have a racetrack-like memory. This is what we are trying to do with skyrmions. So we had the skyrmions, we had the chiral skyrmion, and what we wanted to ask ourselves with the samples that we asked for Matthias, does chiral molecules on top interact with those chiral skyrmions? So we have the phase transition, which can measure in the Kerr microscope. Those are the stripes. So this is a ferromagnetic phase. This is a skyrmionic phase, and we have the phase transition. And he asks the first question we asked, did this phase transition of this hysteresis loop change when we absorb chiral molecules on the surface? And the answer is, of course, yes, as I told you, but of course we can put many dirty things on the surface and reduce the temperature, and this is what we got with same kinds of linkers, but with non-chiral molecules. But when we have chiral molecules, because of those interactions, we see an increase of the transfer or the transition temperature from the ferromagnetic phase to the skyrmionic phase, which means those chiral molecules couple stronger to the ferromagnetic phase, as we saw before. A nice thing that was done at Mainz was that when we change the magnetic layer, or we switch the magnetization of the skyrmions, in one case, this is a diffusion length that was calculated for clear flame in orange, and for chiral molecule adsorbent tough in blue. And depending on the chirality, you can see that it can enhance, couple to the chirality. This is a stronger coupling, less movement or pinning of the skyrmions. And this is the opposite effect with the opposite chirality. So notice that the chirality is preserved, but the scales are much different. In order to see a skyrmion, we have small skyrmion, of course, of nanometers, but we don't see them in the Kerr microscope. So we couple here a small diameter of chiral molecule, which is about 1 nanometer, to a skyrmion, which is could see in optical microscopy, which is few micron, but still the coupling holds on. So it's a very interesting and efficient, effective coupling. We can use a gate, and the gate is quite interesting because with a gate we can induce electric dipole, which is enhance a spin dipole, and we can take a skyrmionic area, put a gate with the chiral molecule, so induce a spin filter, and change it back to a ferromagnetic area. And if we move the voltage, we go back to the skyrmionic phase. So we can take a skyrmionic phase, induce electric field through the chiral molecules, induce spin polarization, and change the phases of the ferromagnetic phase. And in principle, you can have a nice drawing. You can have change. You see change in domain size. You can see change in the cellular domain. You can have a nice picture showing that you can have, in principle, pinning whenever you have a gate. So you can have a skyrmion-like memory with high density. So in principle, this should work. If the skyrmions were smaller, they could have a very small kind of memory devices. Another thing that we want to address along the same line would be that we can use antiferromagnet and chirality. So in principle, you can use non-collinear antiferromagnet, and antiferromagnet are much better to have high density of molecules because you don't have a crosstalk, you don't have interaction between the magnetic domains. The only problem is to write and read them. So usually people use non-collinear antiferromagnet, and then you have a weak Hall effect. And the weak Hall effect enables you to read and write those kind of skyrmionic devices. Sorry. So, since I'm the dean of science, every time I don't touch the screen so much, it closes up, and then I need to put a password. They force me because they say that people will not look into the computer. So sorry, but what I wanted to say here is that in principle, what we say, maybe by putting a gate through chiral structure, we can enhance the ferromagnetic phase, the surface ferromagnetic phase, for a short time, whenever you put the voltage to the chiral structure and have a better signal to noise ratio. Of course, when we remove the voltage, we want to go back to the antiferromagnetic phase to prevent crosstalk. So this is the experiment we did. And indeed, this is what we saw. We saw that this is a gate voltage, and this is a chiral molecule through the gate. This is the antiferromagnetic manganese-3 tin we got from Stuart Parkins. And this is a gate through the chiral molecules, and we measure the whole voltage whenever we put the gate. So you see, without molecules, we have a very small signal, which is due to the collinear phase, but with chiral molecules, we have a very large signal because we force the surface to have big ferromagnet, and we get this anomalous Hall effect, which we can measure whenever we have a voltage. Here you see that it's only when we put the voltage. This is the voltage, this is time, voltage on and off. The blue one is with the chiral molecules. The red one is with achiral molecules, and the green is with achiral molecules. And you see a much better change in the Hall voltage wherever we put chiral molecules through the gate. And of course, you can change Hall voltage if you have a weak Hall voltage by changing just by a standard Hall voltage by changing the density of states. We show that we have very small change in density of states by measuring Rx6. So it's not the change of the N, it's a really change of putting weak ferromagnetism on the surface and getting a anomalous Hall effect on the bottom. And we have very particular temperature dependence, which I don't want to address now. But in principle, what I've shown you so far that we can do very simple spintronic devices, very efficient spintronic devices, but we can do also use it on the exotic material we all work on, and with the chirality we can get the effect of putting surface or ferromagnetic surface which will interact with a ferromagnetic, anti-ferromagnetic, or even paramagnetic, as we see here. Those are the particles I told you about. Those are paramagnetic particles, super paramagnetic iron oxide particle. When we put chiral molecules, we get this resist, we get a ferromagnetic phase. When we don't have chiral molecules, we don't have a hysteretic phase, and this is super paramagnetic. So in principle, and this enhances by a gate. So in principle, you can change between domains, topological domains, by those chiral gating and get some advantage to use those kind of particles. So I want to address two things before giving time to questions. The last thing I want to address related to spintronics is saying how could we do or build an interconnect between the spintronic devices using those chiral effects. And the other thing I want to show is a few applications and why did I get some price of green energy, because the nice thing about it is that we study the origin of life or why spin is important for life, and we studied spintronics, but it got to energy environment because spin is important also there. So just how to do an interconnect. The interconnect or have an efficient spin transfer is using chiral gold. The chiral gold you can use by mixing amino acid like the snail with metals, not with oxide. I'll show you how to mix with oxide. With electrolysis, putting chiral molecules in a solution, you can mix it with metals. And actually, those metals are very interesting because they conduct heat better because they have less scattering through chiral phonons. And they conduct better. If you take a thin metal gold and put chiral molecules on top, you can get better conductivity. So this is one option. The other option is to use superconductivity. Here you will get a surface triplet state, and then maybe couple at low temperature between two ferromagnets. So those are works which I'll not address now. But this was done with Chen Alpern and Jason Robinson, and this was done with Bina Kalitsky, where we use squid to show that whenever we put chiral molecules, we have edge states around those chiral molecules because we think we have a different order parameter. So what about the chiral gold? The chiral gold is just mixing amino acid with the gold. We do an electrolysis. You can mix D or L. You can get opposite polarization. But then we saw something very particular. We have very low resistance until 4 microns, and then the resistance started to increase. We thought maybe we have ballistic or almost ballistic transform until 5 microns because it's spin selective, because we have spin transfer of spin. This does not relate to temperature. So the experiment we did is measuring a high frequency AC signal. We're saying here we have a Hall bar, and we measure the anomalous Hall effect by putting very high AC signal, AC current. And we claim that if it's very slow, so we have the spin time to transfer, so in one side of the cycle, we'll have one side of anomalous Hall effect. The opposite side, because of its chiral, you will have an opposite signal, and it will average out. But if you go very, very fast, you will start with half of the spin going through, but it will not be able to change, and it will get a zero signal in the AC response of the anomalous. And this is exactly what we see, that we see a decay of the response of the anomalous Hall effect. If we go very, very fast, we'll see, we call it anomalous topological Hall effect, because first of all, the current first to have one spin go through, then additional electron gets scattered from the spin. So we have a standard anomalous Hall effect, but it's not as we put from the top organic molecules and a magnetic defect. We induce this spin polarization and get this kind of scattering. So in principle, we get from that, didn't put the main results, we get about a few 5 microns of coherence length by measuring this kind of effect, which relates to this kind of spin polarization, because for spin polarization, we are reducing scattering. We get about few nanoseconds of spin lifetime and about, depending on the current, about 5 micrometer of coherence length at room temperature. I want to end and give some time for questions. I understood that the talk should be about 50 minutes with some applications that could be done with this kind of the CISS effect. And I want to address 2 other kind of applications that could be done. Pure drugs for separating enantiomers. It's working very efficiently. We have a signed paper, but it's a surface effect. So you need huge surfaces to separate an Avogadro number. So it's nice, but it's not very efficient. But green energy, in principle, is something that the green energy, in principle, is something that it could be very efficient, because when green energy, if you think, let's talk about water splitting, you'd start, let's say, talk about electrolyzers, water splitting, but it's true for fuel cells, batteries, and other things. We just start with water, which is H2O, and it's a singlet state. You go to O2 and H2. H2 is a singlet state, but O2 is a ground state, is a triplet state, so it's a spin forbidden process. So in principle, if you coat one of the electrodes with chiral molecules, you will enhance the efficiency by a factor of 2, because you don't throw random spin. You need a multiple spins to do the effect, and you need the 2 spins which go to the O2 will be aligned. And why it is related to the origin of life, and with this I will close the talk and give time for questions, because in respiration and photosynthesis, this is the same effect that we have in electrolyzer and fuel cells. Again, we split, we have a multiple electrode process, and we align the spin, we get much bigger efficiency. So with that, I think it's important, and it also gives us, the startup companies that we have, is actually dealing with green energy, and by other effects such as cooling by chirality and reducing resistivity. So with that, I like to summarize. We saw that with Chiral, with the CISS effect in spintronics, we have a simple way to solve material and content problems in spintronics. We can go to very small devices. We can have very efficient devices with 100% spin selectivity. Then you can use also the MICAF effects, the interaction with the surface through gate or without a gate, to couple to fermions, to superparamagnetic particles, or to antiferromagnets, and superconductivity as well. And with that, I like to thank you for attention and give some time for questions.
So thank you very much for a wonderful talk. That knew us. So we have time for questions. Dima, you may want to start, and then we'll go to Yinan and Abub. And then please raise your hand in the audience if you want me to ask the questions. Yeah.
Yes, Yossi, thank you so much for the super interesting talk. Yeah, as always. I wanted to ask you a little bit about something you said in the beginning, is that CISS is always associated with the lack of time reversal symmetry. I would like maybe to push back a little bit on this. Angela and I have been thinking a lot and discussing this point, and also there is some very nice work by Olga Smirnova, maybe you know, recently. I think that if you have chiral medium and you send electrons through it, you will have polarization, and this is your basic CISS effect. And this,
I agree with that.
This does not need to involve any dissipation.
Okay. So let me answer. I'm not saying I agree that I'll let you continue with the question, but I agree that it does not always have to involve dissipation. What I'm saying that in the usual CISS experiment, which use usually molecules at room temperature, the coupling of the angular momentum of this, it's like it is better to chiral phonons. This is dissipation. I'm not saying that you cannot find condition usually at lower temperature, which does not need dissipation. And this is actually why I claim that we do see different temperature dependence of CISS. In the standard molecule, if you take the electron wave function, which is about half a nanometer, it's about the chiral pitch, it's a non-local effect. So it's very similar to what we see in metamaterials, I think, in chiral structure. So there you usually involve dissipation, but I completely agree with your remark.
Great, thank you.
Let's see, Kiana, you had a question first, and then we'll go to Volker, and then. Okay, Kiana, can you maybe okay, go ahead. Yeah, go ahead.
So I wanted to ask, how can we say that this chiral enhances numerically select which spin to pass to, let's say, for left-handed or right-handed? So what type of spin it will filter?
Okay, so this is a very good question, and this relates to what Dima was taking. It also depends not just on the chirality, but also the polarization itself. It's like if you want to measure that, it's like asking what will be the optical activity of a chiral structure. It depends on the polarization, the magnetic polarization and the electric polarization. So actually you can have, and of course, the secondary structure and the real structure, it's very hard to predict, as it's very hard to predict the standard CD. You could do optical measurement and follow, and what we'll get in the optical measurement, you will get in the CISS effect. But it's a multiple particle picture. It's a non-local effect, and it relates to the polarization. There is a very nice experiment that was done by Christian Tegenkamp, and he showed that you switch the polarization of the same molecules and you get opposite CISS effect. So it's a richer effect than the standard. It's a very nice experiment.
Another question is that
actually this is keeping one, Gaina, so because there's a lot of questions.
Switch the polarization.
Let's just keep it to one question and then we come back if we have time, because there's a lot of people here. Hanbub, can you please ask your question? Yeah. Okay.
Hi, thank you for your presentation. So in the IV curve, you showed the CISS effect. You showed very huge polarization, but it seems the current level is very low. So I think so still this is useful for application because too resistive. So
yeah, the current is very low because it's a large barrier of oxide. You're right. We can reduce the barrier. We have tried that, but then the spin polarization is lower. But in principle, and I didn't show that, you can mix conducting atoms or conducting material with a barrier and have both spin polarization and conductivity, not 100% spin conductivity, but very, very high. So it needs to be optimized, and this needs to be within. I think if some company will take that, it will be better because doing.
Okay. Can I think like there's a
because we need to move on to the next one and maybe we'll come back.
Okay, sorry. Yeah.
Okay.
Thank you.
Fokker, go ahead and
Yeah,
ask your question.
thank you very much for this very nice talk. I have a question concerning the electron and the photon interaction. Are you saying that this CISS effect is supported by a molecular vibration? So like the helices must vibrate in that way, or do you have a feeling about the photons which are needed?
Yeah. So in principle, again, it's related to Dima's question, depending how you preserve angular momentum in the system. But in standard high temperature, yes, I would say exactly that, because you can think about it as Berry phase. Molecules don't have a Berry phase, they suddenly generate a Berry phase, so you get angular momentum. Somehow the angular momentum need to preserve by the interaction of the molecule with the electrons, wave function. It's a full wave function on the chiral structure. And this interaction generates chiral phonons, and usually, if this is a mechanism, the higher the temperature, the better the CISS, and there are some experiments like that. If you have a different systems, then you don't see this kind. Go to lower temperature or different systems, sometimes you don't see this kind of temperature dependence. But in standard CISS experiment in organic, yeah, I would say exactly that. I want to say also something about polarization. If you take a molecule, put very dense material with random polarization, let's say you put the same bond for the top of bottom, like what the recent experiment by Lata, you won't be expecting to see the CISS effect exactly as you won't be expecting to see a CD signal.
Okay, thank you.
Let's go to next to Sitze and then to Gernot after that.
Yeah, thank you very much, Yossi, for the very nice talk. So my question is basically connecting the results you show on the very high magnetoresistance in aluminium oxide, the chiral, and the experiments you show after that, because if I'm correct, those are basically equilibrium type experiments, right? There's no charge current, and your magnetoresistance is also very strong still at zero bias. So it seems that there is a specific coupling between chirality and magnetism, and that is really the main point of what CISS is doing in these experiments. So can you comment on this? Because, so far, I think this is one of the bigger challenges to understand this.
Yeah, I think it's not an equilibrium phase. The coupling starts by generating a dipole moment, which is like we have in van der Waals, but it also, many of the experiments you observe the molecule. So you get the spin polarization, which is not stable, but then it interacts with the substrate and you get like exchange interaction. This stabilizes the system. It's a metastable phase, but it's strong enough to stabilize the system and to enhance the domains within reason. Within reason, but what I'm saying, don't try to flip your fridge magnetization by putting some chiral molecules on.
Yeah, maybe a very short follow-up. So the results you showed on this flipping the magnetization of the thin cobalt layers by different chiralities, right? Is that persistent? Let's say you make the sample and then you measure it, and then you measure it, I don't know, 3 months later, you have it still flip the same direction?
No, it's not persistent, and that's a good question. And actually, we have a paper that with Nir Bargil. We put it on an envy center. On an envy center, the diamonds, we put the magnetic surface and the chiral molecules, and within time you can see that this magnetization decays after a while. Both the molecules get tilted, but that's why I'm saying it's a metastable phase which is stabilized by those kind of interactions.
Okay, yeah, thank you very much.
Okay, and then let's go to the last question to Gernot.
Yeah, for the microscopic understanding, what is the role of the spin-orbit coupling?
Okay, so first of all, you need spin-orbit coupling to break the symmetry, but the spin-orbit coupling in principle of chiral molecules, if you use it, is very weak, but I would say we have an effective spin-orbit coupling by transferring electrons because of several reasons. The first, I told you that it's a multiple electron process. The second is that the electrons are coming even with very high energy, or I would say the second is the non-local effect, the wave function optimize over many atoms, so you should calculate all that and get higher spin-orbit coupling, as you get for twisted layer graphene and other cases. And this is why when you go to very high energy, the wave function is very small, and you get again local interactions. And so in principle, spin-orbit coupling is important, but it's not the standard spin-orbit coupling that is done. So people either use an effective spin-orbit coupling that comes from nowhere, say they give a factor of 100 or 10, depending what's the mechanism they use, or we should go back to the drawing board and do a better effective calculation and do try to add all the effects that I would suggest that the people are suggesting to this calculation.
So it's more on the basis of an atomistic approach and not effective medium theories or so.
It's an intermediate. It's not just a single atom, because a single atom would be too weak, but it's not a medium. But this is what I try to say about line local. It's a stronger effect than expected. Also, you should think that the electrons are coming at very high energy and moving the 1s electrons and generating a larger spin-orbit coupling than expected. But the spin-orbit coupling is giving you to the direction, but you need to calculate the right spin-orbit coupling, which I think we don't do it so far.
Okay, thank you.
Good. Okay, I think we have, if you have a couple of seconds, maybe Stitze, would you like to ask your second question that you had by any chance? I'm not sure if you're still online. Yeah, go ahead.
No, I was not the one with a second question.
Sorry, that's right.
Sorry.
Hanbub, you already had, yeah. Hanbub, did you have the second question? And then Gianna, you had a second question, maybe?
Yeah, I would like to ask about the water splitting efficiency, the coating with enantiomer molecules. You said it's a factor of 2 enhancement over the standard anodes.
Okay, I didn't put the results here because I said I will talk only about spintronics. The question is what you call standard. Because there are, if you just take random electrodes like nickel, yeah, the factor is almost 2 and it's enhancing by a lot. But people in industry are using heavy metals, which align spins in a sense and it's expensive, but get better results. So there, of course, the improvement is less than that. But we can get a large effect, and actually we can do that 30%, or depending if you count capacitance or current, by doing this kind of coating, and also in batteries and oxide batteries. So the factor of 2 is just when you throw random spins and you ask yourself what is the chances for having these 2 spins aligned. It's 2 out of 4. But usually people are doing better than that by choosing better electrodes with magnetic domains or other things.
Okay, thank you.
I think we reached the hour, so I think we should let you on this. You have Yossi, you're a dean, so you have more meetings to go to, unfortunately. Yeah. So I wanted to thank you again and thank all the 90 of you that were live with us, and then also the rest of you that will watch it later. And thank you all of you once again to be here, and thank you Yossi for this wonderful talk. I'll stop now the streaming there. There you go. Now we can say anything you like. And once again, it was a great talk as always. It's a wonderful topic that is still going to be exciting for many